Hello everyone, my name is Alex Tomsic. I'm the Director of Engineering for Red Wolf Reliability. This is the second in a series of videos that I'm putting together to talk about our Voyager FDS sensor. In this video specifically, we're going to talk just a little bit about the sensor operating theory. So talking about the sensor operating theory, we're going to talk about the sensor function as well as introduce the idea of dynamic strain. So in the first video of this series, we talked a lot about static strain, what it is and how it's calculated. We're going to kind of talk about the distinction between static and dynamic strain and then discuss why the FDS sensor only measures dynamic strain. To serve as a little bit of a refresher, just remember the FDS sensor was designed for health monitoring of fluid film bearings on turbo machinery. The FDS sensor measures dynamic strain of the bearing housing due to load from the rotating shaft. And to accomplish this, the sensor is mounted adhesively to the face of the bearing with the sensor direction pointing towards the center of the shaft, so that the FDS sensor can experience the strain that the bearing experiences in the radial direction. In later videos, we're going to talk about locations to mount the FDS sensors specifically. To recall, the strain is the measure of a body's change in length compared to its original length in response to a load, and it can be calculated with the equation below, where you divide the change in length divided by the original length to calculate strain. So in the first video, we talked about static strain, where you have a static load that's applied and its magnitude is unchanged over time. In this video, we're going to talk about dynamic strain. So as an example, we're going to take the same beam in the last video that was used in the last video, where you have a beam that's fixed on the left side with a load applied to the right side. But in this case, that load applied to the right side changes over time. It's an oscillating load. Okay? So what that does is sometimes that load acts in tension and it pulls the beam and elongates it up to a maximum of 0.25 inches. Other times, the force acts in compression and it compresses the beam down to give you a change in length of negative 0.25 inches. So if you looked at that change in length in a total measurement, you would have 0.5 inches peak to peak, where peak to peak is basically taking the maximum amount of displacement and the minimum amount of displacement and measuring between them. So if you took that peak to peak displacement of 0.5 inches and you divided it by 12 inches, you would get that the total amount of dynamic strain the beam experiences is 0.42 strain peak to peak. So this animation is from a finite element model following the same exact beam. So sometimes the force acts in tension and it elongates the beam and it grows to the right. Other times the beam is compressed by the force and it compresses down to a smaller length, as shown in this animation. The blue image of the beam that's superimposed behind it is actually the undeformed model, so you can see where the neutral position of the beam, if no load was applied, would be. So if the tip of the beam is near that neutral position, you'll notice that the color of the contour is purple. That purple color is basically denoting zero strain across the beam. As the beam is either put under tension or compression and deforms to its maximum or minimum length, you see a lighter green color in the contour. That lighter green color is basically the maximum strain amplitude that the entire beam will experience. Now, if we were to place the sensor on that beam and adhesively mount it to measure the strain, the strain of the bottom plate of the sensor is what we're actually measuring. By adhesively mounting that bottom plate to the beam, we're trying to force the bottom plate of that sensor to undergo the same deformation that the beam undergoes. So with knowing that, we can then measure at a fixed interval the strain at any given point in time, and we can plot that on a time waveform. So because the FDS sensor is a vibration sensor, the FDS sensor can provide you with a time waveform and any other vibration plots you would ever need to diagnose problems. In this case, we have, in this example image of a time waveform, we have a maximum strain of 1 strain and then a minimum of -1 strain. And you can see that that's occurring at a fixed frequency where it increases over time till it gets to a point and it smoothly decreases in a sinusoidal fashion. Now, if you think about it in a bearing, right, rotating equipment by definition will have cyclic forces that it creates and that act upon its structure. So those cyclic forces are why the FDS sensor has to measure dynamic strain instead of static strain. Since we're more interested in fatigue instead of failure due to just pure loading, we'll measure dynamic strain of the bearing housing. So in this example animation, again, this is from a finite element model, we have a cyclic load that compresses the bearing and then releases at a certain rate. And if you can see from that, your strain amplitude will vary at that bottom dead center location on that bearing housing over time. So the big thing when mounting an FDS sensor is we need to make sure that we mount that FDS sensor in a location that we expect to see strain. So in this animation, the area that's shaded in the light green is where the maximum strain is actually occurring because of the load that's applied to that bearing. So we need to make sure that we can measure the dynamic strain of a location within that load zone as close to the inner diameter of that bearing as possible. I appreciate anyone that watched this video. The next video in this series is going to show an example of dynamic strain being collected on a cantilever beam using the FDS sensor with a portable data collector. We're going to use that just kind of as an example on how you can set up the measurement with the FDS sensor and where to expect kind of the highest strain amplitudes on a cantilever beam, just as a good example of real data being collected. All right, thank you very much.